Let's take a moment to explore that decision boundary that we played with quite a bit in this lecture. So this is one where 1.0 times number of awesomes minus 1.5 times number of awfuls is equal to 0. In this case, all the points to the bottom of the line have score of xi greater than 0, so they're all labeled as positive, and all the ones on the other side have score of xi less than 0, so we label them as negative. But let's think about the probabilities a little bit more. So if we take this point over here, it's close to the boundary, but it's on the positive side. So we should be outputting probabilities that are greater than 0.5, but not that much greater than 0.5. So let's see what the score looks like for this one. So I looked at a score of xi for this one, and we can measure it directly. So it has 4 awesomes, so those count as 4. And it has 2 awfuls, so those count as minus 3. So you have, the score is 4 minus 1.5 times 2, which gives you a total of 1. And if you push that through the sigmoid, you realize that the probability that y is equal plus 1, given this particular xi, is equal to 0.73. And you can read that from the graph as well. So if I go like this and I push it to the right, I should get 0.73. Now, if you take another example that's further away from the boundary, like this one over here, where I feel more sure, more confident, the probability that y equals plus 1 should be higher. So in this case here, the score of xi is 3. It has 3 awesomes, no awfuls, which implies that our prediction, let's say p hat of y equals plus 1, given xi, is 0.95, which is much larger than the one that was closer to boundary. So it's something that it's more like this, 0.95. Very good. Now let's take a final data point on the other side of the axis. So if you take this data point over here and you compute its score, so it has 1 awesome, so the score of xi has 1 awesome, so that counts as 1, but it has 3 awfuls, so that counts as minus 1.5 times 3, so that total score is minus 3.5, so it's very negative. We should be very sure that it's a negative example, so the probability that y equals plus 1 given this particular xi should be really low. So we're at minus 3 here. The probability should be really low, you can see from the graph, and it turns out that the probability is 0.03 when you push it through the sigmoid. Extremely low probability. It makes sense. A review with 3 awfuls is just awful. Now that we've explored the decision boundaries that come from a logistic regression model and the notions of probability, let's explore a little bit more the effects of the coefficients that we learn from data, both on the boundary and also on the confidence or the sureness that we have about a particular prediction, on the actual probabilities that we predict. So if we take a very simple model with just 2 features, number of awesomes and number of awfuls, and we look at the coefficients of those features as well as the constant W0, let's see what happens. So if that W0 has coefficient 0, then what we have is that the probability of y is equal to plus 1 given xi and w, this particular W0, is given by the curve below. So we see that if the number of awesomes is exactly equal to the number of awfuls, then the score of the two cancel out, and we have a score of xi to be exactly equal to 0. So that gives you a predicted probability of 0.5, just like we saw. Now, if you have one more awesome than you have awfuls, then that difference becomes 1. And your prediction now of the probability of being a positive review, just by having that extra awesomeness, is 0.73. Now let's see what happens if you change the constant. Now, if you change the constant W0 to -2 and keep everything the same, you see that the line has shifted to the right. So now what happens is I need the number of awesomes to have 2 more than the number of awfuls for that prediction to be 0.5. So for the probability that y equals +1 given xi and w to be 50-50. So in this case, awfuls count a lot more negatively than the awesomes, or at least that has that extra constant. Now, if I keep W0 to 0, but I increase the magnitude of the parameters, I get a curve on the right, which is similar to the curve in the middle. So if the difference between the two is 0, I still predict 0.5. However, it grows much more steeply. So in other words, if you just have one more awesome than you have awfuls, you're going to say that the probability of y equals +1 given xi and w's is almost 1. So the bigger you make the parameters in magnitude, the more sure you get more quickly. And the amount you change the constant, you're kind of shifting that line to the left and to the right. Now we can see our logistic regression learning problem. So I have some training data, we extract some features, we have this ML model that says the probability that a review is positive is given by the sigmoid of the score W transpose H, which is 1 over 1 plus e to the minus W transpose H. And when I learn a W hat that really fits the data well. So next, we're going to discuss the algorithmic foundations of how do we fit the W hats from data.